So everybody has been talking about the Psyllid haplotypes. You just saw what's going on in Texas. What we tried to do was to see if these haplotypes, because one of the questions is, so if you have a different haplotype, so what? You know, until you can show there is some differences or no differences, then at this point it sounds to be irrelevant. So the research objective for this TARIX study was to compare feeding behavior and LSO transmission by potato Psyllid haplotype. In this case, we only used 3 haplotypes which are commonly found in the Pacific Northwest, namely Central, Northwest, and Western. We would have a lot to do also the Southwestern, but we could not get access or have a secure colony of the Psyllid. So very specifically, what we looked at was to compare the feeding behavior. Do the Psyllid haplotype feed differently? So if they do they transmit LSO differently? And then we wanted to know, to pinpoint the time it takes for Psyllid to actually inoculate the Liberibacter into a potato plant and induce zebra chip. So the research approach we used was mainly using the electric penetration graph technology to try to see how these insects feed. The EPG technology, basically, it's very simple. You have a plant and you have a tiny insect, and you glue the insect, you put a wire, and then you basically electrify, just the insect, and then the electricity comes, go through the insect, and then go through the plants, and from the plants go through back to the machine, complete the circuit. And so when the insect, this happens, you get this electrical resistance which changes. So if the insect is feeding, you get the resistance changing, and when it changes, you get this kind of pattern, kind of these cartoons. It's like your heart. Then you start seeing this very specific pattern as we are doing this kind of specific activity. It's like my voice usually doesn't change. Even if you put me somewhere behind the room and I start talking, I'm going to say, "That's Joe." The way we feed basically comes the same behavior. So these insects also, they have very specific behavior, and this becomes kind of constant. So, and these are called waveforms, and these waveforms are very, very characteristic for Psyllids. So here is the cartoon I was showing. This is the actual setting for the EPG in our lab, where we do all these, trying to electrify these Psyllids, these insects. Of course, you have to really send a very small electrical current, otherwise we are going to die, and these will just move around. So anyway, one of my former students called Pearson was the first person to develop waveforms, waveforms for the potato Psyllid. So, and what he came up with a bunch of different feeding behavior waveforms, and here they are the main ones. They see, basically, if the insect is, if you put this insect on the plant, it starts, probing in the plant. Many people who think it's like a needle, it's going to go inside immediately, but it doesn't work that way. They keep digging slowly, and the first phase, it's what we call Stylet penetration, where the insect starts right here. This is a leaf tissue, and so you will see this kind of pattern on your monitor. The insect is trying to probe into the leaf tissue. Then once they get into the xylem, here you can see you get that kind of waveforms if it's a potato Psyllid. So if you are looking at your monitor and you're seeing something like that, the insect, they are just getting into the phloem. If they are, into the xylem. So if they get into the phloem, where Liberibacter is phloem limited, to cause zebra chip, it has to be deposited into the phloem. Otherwise, you're not going to get zebra chip or any infection. So these two waveforms are extremely important. The E1, that's when the cell is feeding in the phloem, and they do salivate in the phloem, which means basically they are spitting in it, injecting whatever they have in the salivary glands, and that's when you have inoculation. So the inoculation happens, even inoculation is happening, we're going to see this type of waveform, whereas acquisition is when they are ingesting the phloem from the plant. So you are going to see this waveform. Basically, typically, these four, there are many more. Pearson described many more, but those are kind of four characteristic, stylet penetration, Xylem ingestion, and then you get to the phloem salivation and ingestion. So when Cole did this study, he used cells from Texas, which are presumably central. So the issue is now we have northwestern, western, southwestern. Do they have the same behavior? So we, just try to look at this. So what we did was we take 12 Psyllids from each haplotype, and these insect adults were starved for about 3 hours before they get hooked to EPG machine. And once we hook them, you record whatever they are doing in 24 hours. You don't have to be there. You hook the insect, you leave, you come back, and then you just go to your computer, you download it, you know exactly what they did every second. So after recording, what Tariq found out was he compared these waveforms. So here we have the study by Pearson. You can see this is Stylet penetration. And you can see the central, the northwestern, and the western. All these waveforms look exactly similar. The same thing was the first time when they hit, they reach the phloem. The first time they contact the phloem, so they will be trying to penetrate the leaves, and once they hit the phloem, these will change. So you can see for the three haplotypes, the waveforms representing the reaching the phloem is the same as what has been described by Pearson. So same trend was observed for phloem salivation and ingestion. Basically, these three haplotypes do reach the phloem same way. The same trend was observed for the Xylem ingestion. They give exactly the same pattern, which translates into they basically feed the same way. Don't see any difference. So we even during the 24 hours, we wanted to see what happens. So if you put them on the plants, how many times do they go into the phloem? How many times they go into the xylem? How many times they probe? And so if you look at this figure here, you can see basically the number of events per haplotype. There's no statistic differences between, just what they do. And so when we looked at the time, a duration, because they can go into an event for twice or three times, but it really depends on how much time they spend doing that. And when we look at the duration during those probes, you can see that basically they are spending almost, statistically there's only difference. They spend the time trying to probe the stylets. They all reach the phloem almost the same time. They spend a little time and then they pull out. You can see they all spend time in the phloem, salivating it, acquiring the bacterium, and feeding in the xylem. So basically these three haplotypes have kind of same feeding behavior. So you can see here they reach, if you put them on the plant, the question was, if we put them on the plant, which one is going to go into the plant first? These guys seem to do the same thing. You can see if we put them on the plant, within 10 minutes, they start probing on the plant. All of them, it was a trend in all these cells we used. So once they start probing, how fast do they reach the phloem? Well, as you can see for the 3 haplotype, it takes about 2 to 4 hours to reach the phloem. Basically, if they land on a potato plant, the first 2 hours, we may not be able to infect because we're not reaching the phloem. It takes about 3 to 4 hours to reach the phloem. How about the acquiring? So they start acquiring about 4 hours once we land on the plant. So the psyllids, once you put them on the plants, it's going to take about 4 hours before they start acquiring the bacterium. They usually do salivation first, which they do about 2-3 hours, and then after they start just ingesting the phloem. So now we knew that they do the same kind of feeding behavior. We wanted to know, how about LSO transmission? Do they transmit LSO the same way, this haplotype? So the way we did this, we took psyllids again, but these came from LSO-infected colonies from the 3 haplotypes, and then these adult psyllids were used EPG, so they sit on the plant, recorded with EPG, but they were given inoculation access period from 1 hour to 24 hours. So 1 hour, 2 hours, 3, 4, 5, 6. We jump to 12, then 24 hours. So every time, like after 1 hour, you interrupt the recording, and you collect the plant, and you collect the insect. Then you maintain the plant to see if you're going to get symptoms. So also the insects are coming from an LSO-infected colony. Doesn't mean they are necessarily infected. So we had to test them, kill them, and test them to verify, to make sure they are infected. If they are not infected, we excluded that. So those plants, all those plants recorded after 1 hour, 2 hours, 12 hours, 24 hours. These plants were transplanted in cages like this, and then we just try to observe for symptoms to see if they're going to develop symptoms. And then, of course, the plants were tested to confirm they have, test for LSO to confirm they infected with the bacterium. So here is the summary of the results. As you can see here, we have 1 hour, 2 hours, 12 hours, 24 hours. You can see the plants showing symptoms. The infection rate is fairly very low during the first 2 hours. So some insects who get into the plant were able to reach the plant and infect the plant. But really it doesn't start until 3 hours. 3 hours, that's when you can see for each inoculation access period, there was no statistical differences among us. So basically, after 3 hours, these insects are going to infect the plant. And it doesn't matter whether they are central, northwestern, or western, which was very interesting. So it looks like the transmission efficiency is similar. So one thing we really wanted to know, we know basically after 3 hours that Jeremy, when he did his previous study, he's shown that it takes about 6 hours for the psyllids to infect the plant. So we have known about this. But these, with EPG, we were able to narrow down to 3 hours. So, which is now good, especially if you have an insecticide. You have to get an insecticide which is going to kill this insect quick enough, within 3 hours, if you're going to do something. So, once we get there, we wanted really to pinpoint how much time, the actual time it takes for these psyllids to inoculate the bacterium. So what we did was, because if you put them for 24 hours, we're going to the phloem many times, you are not going to know which event they used to inoculate the plant. So our strategy was, we kind of limited our data on 3 hours. So we took those insects, we looked at the recordings for 3 hours, and then or less, and then we also tried to identify those insects which had only one phloem salivation event. Only one, because if you have 2, then you don't know which one, during which one they did inoculate. So also we made sure these insects, which fed briefly, the corresponding plants were infected with zebrachen. So at least we're able to identify at least a couple of psyllids for each haplotype. And as you can see here, these insects, it takes about less than 10 minutes, once we get into the phloem, to inject the Liberibacter into the phloem and cause zebra chip. You can even see, like in this northwestern, it takes about 3-4 minutes just for them to, be able to put the bacterium once they reach the phloem. So you have basically 3 hours for them to start digging until they reach the phloem. Once they get there, basically it's just a game. It's just a couple minutes and finished, done. So this was very interesting because I know many people who are asking. Unfortunately, we didn't have a southwestern haplotype, so we can show this. I believe we are getting a colony, right, Kylie? So we're getting a colony, so hopefully we can follow up with the southwestern, but at least for this one. Now, this has a lot of implication, at least when you're in the Pacific Northwest. Most of the psyllids we find up in the Northwest, they are northwestern or northwestern western. If you come in Washington, Oregon, most of the psyllids around there in potatoes or the bitter-sweet nightshade, they are northwestern. As you move to Idaho, you have more northwestern during the winter, but once you get into the potatoes, you tend to see more western than northwestern. So before 2011, we didn't have any zebra chip in Northwest. And most of the psyllids which were there were northwestern. And the reason why we didn't get zebra chip, it's not because we didn't have psyllids. It's because the psyllids were clean, were Liberibacter free. So it looks like the northwestern psyllid had not come across Liberibacter before. But now we are getting infected psyllids, which means, it's going to be moving in, because northwestern is as efficient in transmitting Liberibacter as central as western. So I suspect southwestern probably does the same thing, even though we have not got a chance to do that. So if you are basically a grower in Northwest, you have to watch out, because over time, as Liberibacter spreads, we may have issue. So the take-home message from this study, this portion of study of Tariq, is that these psyllids basically feed in a similar way. And the also transmission of Liberibacter seem to be, almost the same. What surprisingly now, we used to use again 6 hours as our minimum inoculation access period. Bad news, it's even much lower than that. And it takes basically a few minutes for these insects, once we reach the phloem, to just infect the plant. So I would like to, the funding came from SCRI. Of course, USDA contributed to that. Washington State University did pay some portion for Tariq, and we got money to do this from the Northwestern Potato Research Consortium, specifically the Washington State Potato Commission, to do this work. I think I'm going to stop right here.